Hey guys, it is your boy Tariq Mauser, and I will be teaching intermediate algebra. But before we begin, let's just go over an overview of what we will be learning over the next week. Day 1, today we will be doing set theory and factorizations. Day 2 will be polynomials. Day 3 will be functions and functional equations. And day 4 will be inequalities, so you can expect that over the next 4 days. I plan to make each lecture about 20 to 30 minutes roughly. But I do plan to go fairly quick, so don't be afraid to pause or rewind if you ever feel like you need to. We start off with sets and set theory and a definition of sets, which is a set is an unordered collection of objects, and a set itself is a mathematical object. One way of thinking of a set is like a box where you can put things in. So some examples of sets are the following. Here we have a set with squares, rectangles, and rhombuses and parallelograms in it. It's just a set which contains these words or items you can think of. But obviously in maths we usually care about numbers, so you can have a set with the numbers 1, 5, 2, and 3. Here I'm demonstrating that here you can have a set with a set in it. So imagine that this is a box with a box that contains 1, 2, and 3 in it, as well as, loosely, the numbers 7 and 10. Now also sets don't care about repetition. So over here what we're concerned with is that this is the set with 1, 1, and 2, but that's exactly the same as the set with just 1 and 2, that this repetition of 1 doesn't matter at all, that you can write it like this, and this is how we usually write it, without repetitions. This is a very special set also, called the empty set. The empty set is written like this. It's not written like this is something different. And you can think of the empty set as just a box with nothing in it. So it's the set that contains nothing. What this means over here is a set which contains an empty set. So what you can think of this thing as a box which contains an empty box. Okay, I say over here that you can also write the empty set as just empty brackets, but nobody really does this, but you can think of the empty set as this, an empty box. Next, what we're concerned with is the element of symbol over here. When we write something like this, red 1 is an element of the set, what we're saying is that 1 is inside the set. Okay. When we write 7 is not an element of the set, that's what the element of the cross symbol means. I mean 7 is not in the set, and you can clearly see that. The set has 1, 5, 2, and 3, no 7s. Some special things on how this works. You remember you can have sets with sets in it. How that works with the element of set is that you need this exact thing to be in the set. So for example, 1 is not an element of the set, because there's no 1 loosely in this box. There's a box with 1 in it, but that's something different. So here we can say that the set of 1 is an element of here, because we have a box with 1 in it that's in this box. Okay. Next we'll be dealing with some set operations. There's two main ones. The first one is the union that joins two sets. Essentially, if you have two different boxes with things in it, it puts all the things in one box. So over here we have a box with 1, 3, 2, union with 71, 72, 73, and we get a set with 1, 3, and 2, as well as 71, 72, and 73. Here we have the set 1, 2, and 3, union with the set 1, 5, and 6, and we get the set with all of those things in 1, 2, 3, 5, and 6. Notice here that there's a 1 in this set and in this set, but there's only 1 in here. That's because, as you should remember, sets don't care about things being there multiple times, so we write the 1 in there only once. Next we have intersection, which gives the overlap of the two sets. It'll be more clear in an example. Over here, if you want to intersect these two sets, the set 1, 2, 3, 4, and 5, and 3, 4, 5, 6, 7, you get the set 4 and 5. That's because 4 and 5 are the only two elements of these two sets that are in both sets, as you can see here. Over here we have the set 3, 5, 9 intersect with 1, 4, 2. What you'll notice is that there's no elements in either of these sets that are in both of the sets, so you get the empty set. It's the set with nothing in it. One way of thinking of this is you can think of union as or. So you're saying what is in this or this, and that joins together. And you can think of the intersect as and, what is in this set and this set. So 4 is in this set and this set. Next, we talk about subsets, which are often talked about in combinatorics. The set Y is a subset of X if every element of Y is an element of X. written y subset x. You can remember this as this kind of looks like a less than or equal to sign, that y is the smaller set of x. So for example, 1, 3, 5 is a subset of 1, 2, 3, 4, and 5. That's because 1, 3, and 5, the set, is completely in the set. It has a 1, 3, and 5. A counterexample is that 1, 3, and 5 is not a subset of 1, 3, and 4, because 5 is in this set, but not in this set. Next, we'll be going to some common sets, and this will really be used quite often. We'll be used in day 2 on polynomials and day 3 on functions. The first, you probably know these by different names. So the first set we're going to talk about are the natural numbers, which is denoted by a fancy n. These are all the numbers that you use in day-to-day life with counting. It's 1, 2, 3, 4, 5, 6, and on and on and on. Next is the whole numbers, which is just the natural numbers with 0. It's essentially that. Look, the symbol is n here. This is just n with the 0. Next, we have the integers, which are the natural numbers as well as the negative numbers. So 1, 2, 3, and -1, -2, -3, including 0. The next two sets are more special sets, which we'll be working with more often in algebra. Often you work with this set and this set in number theory. But Q, the set of rational numbers, is the set of all fractions. We have a and b for a and b integers with b not equal 0, because remember, we can't divide by 0. So that includes all of these numbers, so 0, -1, 1, and so forth, as well as fractions, so a half, -7/11, and so on. It doesn't contain weird things like the square root of 2 though, because those aren't fractions. Then we go on to the real numbers, which are all the numbers on the number line. And that's the best definition I can give you right now. Actual definitions of the real numbers are often quite complicated, but this definition is good enough for our purposes. It's all the numbers you can probably think of. 0, 1, -1, a half, pi, square root of 2. The reason why the rational numbers and the real numbers are more important in algebra than these things is because Q and R are what we call in maths fields. What that means is, if you take an element of Q, so take a rational number, and divide it by another rational number, you'll get a rational number. Same with the real numbers. If you take a real number divided by another real number, you'll get a real number. Unless you divide them by 0, but we don't divide by 0. That's not true for the integers or the natural numbers. For example, if you take 3 and divide it by 2, you'll get 3/2, which is a rational number, not an integer. So you go from z to q while dividing in z. So that's the reason why Q and R are important for us. Notice also that these are all subsets of each other, that n is the smaller set, which is a subset of the whole numbers, subset of integers, subset of the rational numbers, subset of the real numbers. That's what I wrote over here. So these are an increasing order of sets. Last thing about sets is that you'll sometimes come across intervals, and this is just a way to represent a set or describe a set. In the following examples, you should try and remember that the square bracket means includes and the curly brackets means excludes. Why? Well, because if you have a set like this, a, b, what that means is it's the set of all real numbers between a and b, including a and b. Why do we know that it's including a and b? Because we're using square brackets here. So for example, the set 3, 7, square brackets, are all the numbers between 3 and 7. So if you drew the number line from 3 to 7, that's all the things there. So it includes 3, it includes pi, because that's 3.1, roughly. It includes 4, 4.5, 6, and 7, because it's inclusive. We can also have sets with curly brackets, which is the set of all real numbers between a and b, excluding a and b. Remember, curly means excludes. So for example, 1 and 3 means, with curly brackets, all the numbers between 1 and 3, not including 1 and 3. And that's what I've written here. Well, that 1.1 is in it, 2 is in it, 2.3 is in it, 2.5, 2.7, all in this, but 1 is not in it, and 3 is not in it. You can mix the brackets around. For example, over here, you have curly bracket 4 and 6 closed, which is the interval between 4 and 6, so it includes everything between it. It does not contain 4, because curly bracket means exclude, but it does have 6, because square bracket means includes. The main point of this lecture is sets and factorizations, but I want to get some other algebra out of the way first. And these are things that you probably know, but maybe don't know the names of, or maybe you do know this entirely. These are properties of adding and multiplying, mostly. This is the associative property. It says that you can add the numbers a plus b, and then after you calculate this, add c, and it's the exact same as adding b plus c and then adding a afterwards. This is called the associative property. We then have the commutative property, which is that adding a to b is the same as adding b to a. And then the one that we really care about in this lecture is the distributive property, which is if we have a times b plus c, if we don't write anything in the middle over here, it means times usually, that is equal to a times b plus a times c. How you can look at this is that you have an a over here with the brackets, and when you want to distribute out, you put the a to each of the things inside. So that's ab, ac, and you get this. You can also look at it backwards, that you can use it to factorize this expression, which is if you have a common thing on each term. So for here, there's a common a on each term. You can pull them outwards and then leave everything that you had originally in the brackets over there. So the distributive law is also useful because it allows us to multiply out expressions. So for example here, what if we didn't want to add first and then multiply? Because this is what this says. It says add x and y times it by adding a plus b. Sorry, I'll say that again. You add x and y together, you add a and b together, and then you times the product. What if you want it to be so that you multiply first and then add later? We'll see later why this is a useful idea. We can use the distributive law to do this for us. So we first apply the distributive law on x plus y. Over here, we distribute it to that one and that one, which you'll see over here. X plus y times a, x plus y times b. We can then apply this distributive law again on a and b over here, where we can get xa, ya, bx, xb, and yb. You may have noticed that this is basically the exact same as multiplying all pairs. So it's xa, xb, ya, yb. That's all the pairs on opposite sides of the brackets, which we can do with a grid. Oftentimes it's just faster to calculate things like this, not to write out all the steps, and this is often how I look at things, where you can draw a grid with your terms on either side, and then you just multiply every pair. And you can see that this gives xa plus ya plus xb plus yb, so it gives the correct answer. Another example is x plus y plus z times a plus b. We use the distributive law again to get this, and we use it once more to get all these things. Notice that we can use the distributive law when there's three things as well. So they're xa, ya, za, xb, yb, zb. And just to show again that this is the same as just multiplying all possible pairs, you can draw out the grid, a, b there, x, y, and z, and you get all these terms which do in fact match up. So just an example question that uses multiplying out. It's a bit contrived, but I want some examples in. Is that you're given this equation and find all values of x and y such that this equation holds. X plus y squared equals 2xy plus y squared. Okay, so let's try and solve this equation. Set it up, and then we notice that x plus y squared is just x plus y times x plus y. Now this part is important. We multiply this out. So you can do it by the other methods, but you can see that you get x times x is x squared, y times y is y squared, x times y is xy, and then y times x is also xy, because y times x is the same as xy, so we get 2xy. So importantly, x plus y squared is equal to x squared plus 2xy plus y squared. It is not just equal to x squared plus y squared. There's this middle term that people often leave out that's very important. Okay, once we have that, we can cancel some terms, the y squared and the 2xy, to get the equation x squared equals 0. And you can clearly see that since x squared equals 0, we just have x equals 0, which is the solution to this equation. Notice that there's no y at the end of this answer, and what that actually means is that y can be anything. So how you can write this answer is that the statement is true whenever x is 0 and y element of the reals. What this means is that y can be anything, and the statement is true. You can check this by just putting in x equals 0, and you'll see that this side becomes y squared, and this side becomes 2 times 0, which is 0, plus y squared. So this becomes y squared equals y squared. So you can always check your answers in algebra by putting them back in the original equation. Next, I'm just going to justify why we should care about factorizations. And the reason is that the real numbers and the rational numbers have a special property, as that it is an integral domain, which is a fancy way of saying this, that if you have two numbers that when multiplied together gives you 0, one of them have to be 0. So if a times b equals 0, then either a equals 0 or b equals 0. It could be that both of them are 0 also. In maths, all could be always inclusive, so both of them can be 0 also. So this is actually a very useful property, because if you're given an equation like this, which seems very unruly, that xy minus 3x plus 2y minus 6 equals 0, seems like a very difficult equation to use. But with factorizations, that you can factor this into x plus 2 times y minus 3, actually, let me clarify why you can do this. How do you see this? Well, this is, you sort of have to guess that this works. But you can, once you've guessed it, you can check that you're correct by noticing that these two things are equal by multiplying this out. So you can multiply this out by saying that this is xy over there minus 3x, those two multiplied together, plus 2y, 2 times minus 3 is minus 6. So these things are in fact equal. So this equals this, which equals 0. So we get this equation, which using this property, we have two numbers multiplied together, gives 0, which means that either this is 0 or this is 0. If this is 0, then x is equal to minus 2. If this is 0, then y equals 3. You can do that by solving this equation. Set y minus 3 equals 0 and then solve. So notice how we got a nice property like x is minus 2 or y equals minus 3 from this difficult equation by factoring it into something nicer. Okay, so now we're just going to go through a bunch of factorizations, and the best way maybe to learn this is both looking at it, writing it down also after I've explained them, and maybe multiplying it out just to check that they all work. The very first one is the one that we've seen before, x squared plus 2xy plus y squared equals x plus y squared. You should just know this. You should be able to multiply this out to check that this works. The next one is probably the most useful factorization. It comes up the most. All three of these came up at once because they're all just this in disguise. But x squared minus y squared, this is called the difference of squares. So x squared minus y squared is equal to x minus y times x plus y. How you see this? Multiply that, get x squared, you get plus xy, here you get minus xy. So this term that I mentioned previously cancels with it, and then you multiply this one, and you get minus y squared. So that middle term gets cancelled in this factorization to just give you x squared minus y squared. If you're still a bit confused, I recommend multiplying this out and writing it all down to see what happens. Next, we have difference of cubes. It starts off similarly, x minus y, and then you have x squared, so one less than the cube, plus xy plus y squared. How you can remember this equation is by mostly just the general formula, which all of these share the first term with, which is when you have xn to minus yn, your first term is x minus y, so just these two numbers subtracted. Then you have x to the power of n minus 1, so x to the power of this number minus 1. Then the x's, the exponent over here, is going to decrease with each term. So this is going to become xn minus 2, and then the y exponent is going to increase with each term. So there's a secret y to the power of 0 over here, and then it becomes y to the power of 1. And then after that, it'll be x to the n minus 3 y squared, and then x to the n minus 4 plus y cubed, I think, yeah. This goes on and on and on until you reach the other side, which is x to the y to the n minus 2 plus eventually y to the n minus 1. See, the x's are still decreasing here, the exponent, and the y's are increasing. This one's also fairly important. Next is x cubed plus y cubed, sum of cubes. Very similar to this one. The only difference is that there's a plus sign here and a minus sign here. So x cubed plus y cubed equals x plus y times x squared minus xy plus y squared. There's this factorization. I honestly don't think it's that useful. For some reason we teach it. And so x to the 4 plus y to the 4 is equal to x squared plus xy times root 2 plus y squared times x squared minus xy times root 2 plus y squared. Sometimes it gets used. I think it's kind of rare. This one, and this one is a lot more important in my opinion. Then the plus signs are a bit weird. So we have a formula here for xn minus yn for all n. This works always. But this formula only works when n is odd, and I'll tell you why just after I read this. So we get xn plus yn equals x plus y times x to the n minus 1 minus x to the n minus 2y, and then a similar thing will happen here that happened here. The x terms will decrease and the y terms will increase, so n minus 1, n minus 2 times y, plus x to the n minus 3 times y squared, and there'll be x to the n minus 4 times y cubed. The strange thing that happens here is that the sign over here keeps changing. It goes minus, plus, minus, plus, minus, plus, minus, plus, eventually going out over here to plus, minus, plus. It must end on a plus over here. The reason why it must end on a plus is to get the yn term over here, you need y to the n minus 1 times y, and this has to be positive. Otherwise, you'll get xn minus yn. So that's the reason for n is odd, is for this sign change to work, to get plus, minus, plus, minus. If n was even, you'd get, let's say n was 4, you get plus, minus, plus, minus. The last thing would end on a minus, this yn term, and this factorization wouldn't work. So that's why we have this special factorization for when n is 4, which you can use. When n is odd, you'll use this one. You'll notice there's no x squared plus y squared. The reason why there's no factorization for that is because there isn't one, in the real numbers at least. But you'll maybe learn more about that in seniors. Next is a factorization that isn't taught for some reason, but I think is quite useful. It's ab minus a minus b plus 1 is equal to a minus 1 times b minus 1. It's often useful if you have some inequality like a is greater than 1 and b is greater than 1, and you want to prove that this is greater than 1. But we'll get more to that during inequalities. So I think this one's important, this one, and this one is important, and this one's kind of important also. There's some more factorizations. This one's also kind of important. It's just the square of 3 terms. So a plus b plus c squared is a squared plus b squared plus c squared plus 2ab plus 2bc plus 2ca. So you'll notice that this is 2 times all the pairs over here, ab, bc, ca. Should be able to spot this, square this out, see why this works. Next is a factorization that seems a bit odd. It is a cubed plus b cubed plus c cubed minus 3abc equals a plus b plus c times a squared plus b squared plus c squared minus ab minus bc minus ca. Next we have this thing, which this looks like madness. The only reason why we care about this is because this kind of looks nice. And you'll notice that this has a nice pattern to it. It starts with all these numbers positive, x plus y plus z. Then it changes to one of them negative, x plus y minus z. Then the next one negative, x minus y plus z. And then the last one negative, minus x plus y plus z. So this thing happens once or twice. It happens in the proof of one of the geometry theorems that I think it's Heron's formula that works at the area of a triangle. But otherwise, not super common. I guess it's good practice for multiplying out to multiply all this out to get this. I'll warn you that you'll get like 3 to the power 4 terms, which is about 81 terms, which you'll have to cancel into this. Could be useful to know offhand. But honestly, these aren't super useful. You should just know them, because Phil likes it when people know them for some reason. Anyway, let's go into applications of factorizations. So this one. Solve for x squared minus 5 equals 0. I'm sure many of you can just solve this by looking at it, or maybe know a way of solving it, but I'm actually just showing a method here of what you can do to factorize, where this happens quite often, where you have something where you want to factorize it, but you can't because you don't have a difference of squares. And what you can do is you can make something a square. So 5 isn't a square number, but we're not necessarily restricted to integers. So we can say that 5 is actually equal to the square root of 5 squared. Because this is allowed. The square root of 5 squared is 5. So we can rewrite this equation as x squared minus the square root of 5 squared equals 0. Now we have a difference of squares. So we can use our factorization on our previous slides of x squared minus y squared to get that it's x minus y, x minus root 5, times x plus y, x plus root 5 equals 0. Now we can use the property that we're multiplying two numbers to get 0. So one of them have to be 0, which gives us that this is 0, means x equals root 5, or this is 0, which means x equals minus root 5, which is how you can solve these type of equations. Next, we have a more difficult question. It's number theory flavored, which is that we have a and b such that ab minus 3a plus 2b equals 13 for all, we're solving this for a and b natural numbers. So 1, 2, 3, 4, and so on. So solving this directly can be difficult, but we can spot a factorization. What you can, this isn't one of the factorizations taught previously, but it's a sort of common idea of how to factorize, where you have a variable plus a constant times a variable plus a constant. So over here, you can notice that this thing over here can't exactly be factored, but we can minus 6 to get the terms ab minus 3a plus 2b minus 6, so this minus 6 can be factored into this. You can check by saying multiplying out, you get ab, you get minus 6, you get, check that one already, you get minus 3a, and you get 2b. So this is equal to this. Question is, how do you spot that you need this minus 6? You don't actually. You kind of work in reverse. You instead say, I want to factorize this, and I'll add terms if I need to. So what does this kind of look like? Well, it looks like I need an a and a minus... I need an a and a plus 2, because this b needs to be times by 2, and needs to be times by a. So I need an a plus 2, and then you can kind of guess, well, this a needs to be times by minus 3, so I need a minus 3, and I need a b somewhere, so let's put a b there. And you can guess this is a plus 2 times b minus 3. You can then multiply it out and see, oh, I need a minus 6 to make this work. So how do we use that? Because this isn't exactly this. Well, we start with our equation. We then minus 6 both sides, because we're affecting both sides of the equation, so it's still valid, to get the terms that we need. Then we can factorize. 13 minus 6 is 7. And then we can solve it from here. And this is kind of big, but I'll explain what it means. Remember that a and b are natural numbers, so a plus 2 and b minus 3 are also natural numbers, or integers specifically. 7 is a prime number, which means that the only way to multiply two numbers to get 7 is 1 times 7 and 7 times 1. So that means that this is either 1 times 7 or 7 times 1. So that means a plus 2 is either 1 and b minus 3 is 7, or we must have a plus 2 is 7 and b minus 3 is 1. And then we can solve these equations. So let's solve the first equation. A plus 2 equals 1 and b minus 3 is 7. We solve it and we get that a is minus 1 and b is 10. Now notice that our question said a and b are natural numbers, and minus 1 is not a natural number. So this solution isn't valid. So this isn't a valid solution. A is not a natural number, so this solution does not count. We then try and solve the second one, which is a plus 2 equals 7 and b minus 3 equals 1. Solving this gives that a equals 5 and b equals 4. And this is a valid solution. Both a and b are natural numbers. So that's the only solution. This kind of got cut off, but it's hence a equals 5 and b equals 4 are the only solutions. Now I slightly shortened this. You have to do a bit more work actually. Remember I said that 7 can only be 1 times 7 and 7 times 1. That's not true. That's only work if you're working with natural numbers. But technically these are integers. So you have to check minus 1 times minus 7 and minus 7 times minus 1. But it turns out that for those solutions, a will always be negative, so those aren't valid solutions. I just cut it out so that this could all fit on one slide almost. Next we have another question. This is in high school called the sum of a geometric series. And we'll see that we can find a nice formula for this using factorizations. So this is adding the numbers, find a formula for a plus a times r plus a times r squared plus a times r cubed plus a times r to the power 4, so on, plus a times r to the power of n. So this is adding n plus 1 numbers together. So we're going to try and find a nice solution for this. Given that r equals 1, r is not equal to 1. The reason for that will be clear in a bit. Okay, so how do we start this? Well, clearly over here, with all these terms of a, so you could factor this a out, and what you'd get is a times 1 plus r squared plus dot 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 up to r to the n. And you may notice, or that may remind you of a certain factorization, and that's how you're going to start this. This is also important because it demonstrates that 1 to the power of 1 can be written as 1 to the power of anything. So we start off with r to the power of n plus 1 minus 1, and that's the same as r to the n plus 1 minus 1 to the power of n plus 1, because 1 to the power of anything is still 1. And now because this is the difference of n plus 1 powers, we can use our factorization to get r minus 1 times r to the n plus r to the n minus 1 plus dot dot dot. These powers are going to decrease up to 1, which is this thing divided by the a. Okay, but we want this thing alone, so we want to divide through by r minus 1. which is where this condition comes in. Because if r was equal to 1, this would be equal to 0, and we wouldn't be allowed to divide through by it, since we can't divide through by 0. So since r is not equal to 1, we can divide by r minus 1 to both sides to get this. So that's just this term over here divided by r minus 1, and this is over here. It's just swapped around because to make it look like this also. Then what we can do is we can multiply by a both sides to get a formula for this. So we multiply by a to get a plus ar squared up to ar to the n over here, and we have to multiply this side also by a. So this is a formula for this. So a times r to the n plus 1 minus 1 over r minus 1 is equal to the geometric sum. The formula isn't that important. What's actually important is the technique to get there. So it's better if you understand the technique than like the formula itself. And that mostly wraps up for what I have for today. Turns out I was wrong. I've come back from setting the day one paper and talking to the other coaches, and apparently intermediates are expected to know the quadratic formula, so I'm going to quickly teach that here in the speediest fashion possible. Okay, the quadratic formula, what are we trying to do? Well, given any equation, ax squared plus bx plus c equals 0, we're going to try and solve for x. We're going to do this by breaking it up into two steps. The first step is to solve equations like this. M times x plus n squared plus r equals 0. We're going to solve this with normal techniques. Set up the equation, bring the r over, divide through by m to get x plus n squared equals minus r over m, and then square both sides. Now remember here, you get a plus and a minus solution. Because, for example, suppose you have an equation like x squared equals 4. The solutions to that is x equals 2 and x equals minus 2. There's a positive and a negative solution, because both 2 and minus 2, when squared, gives you 4. Okay, after that, you can then just take the n over to solve for x. So what I've shown just here is that given an equation in this form, we can solve for x using normal techniques. Okay, but we have an equation of this form. What we're going to do then, next, is get an equation of this form into one of this form. How do we do that? Well, there's this special factorization. This may seem a bit weird. It's called completing the square, and I'm skipping a bit of steps, just showing you the formula. But essentially over here, if you factor out a, you'll see that this thing over here will become x plus b over 2a squared. You can just verify that this is true by squaring this out and multiplying everything out. Okay, once you have this, you can take this to the other side to get this formula, which you're going to use, that ax squared plus bx equals a times x plus b over 2a squared minus b squared over 4a. Okay, so then what do we do? Well, roughly what we're going to do is we have the equation, we're going to use the substitution to get a times x plus b over 2a squared minus b squared over 4a plus c. Then consider the substitution of letting m equal a, n equal b over 2a, so this part, r equals to minus b squared over 4a plus c, and this part. Then the equation becomes m times x plus n squared plus r. But previously, we said that we could solve these types of equations. So that means if we just think about this equation, like this equation, we should be able to solve it, which is what we're going to do next. So starting from the very beginning again, ax squared plus bx plus c, do our factorization substitution of a times x plus b over 2a squared minus b squared over 4a plus c equals 0. We then take this over to the other side, divide through by a, b squared over 4a squared minus c over a, square root both sides. Oh wait, first we make this one common fraction. So to make this the common denominator will be 4a squared. So we times 4a there and 4a there to get b squared minus 4ac over 4a squared. Square root both sides to have a plus minus there. Then what we can do is we can simplify this slightly with the square root by square rooting the numerator and the denominator. The square rooted numerator stays the same, and the square rooted denominator becomes 2a, because 2a times 2a is 4a squared. And then we take over the b over 2a. So we get x equals minus b over 2a plus minus root b squared minus 4ac over 2a, which is the quadratic formula. It's best to remember the technique to get there, but honestly, if you can just memorize this formula, that's also good. The formula here then for if ax squared plus bx plus c equals 0, then x equals minus b plus minus root b squared minus 4ac over 2a, which is the quadratic formula. There's one special thing about this though. You'll notice we're square rooting a number, and you can only square root positive numbers. So that means that this only has solutions actually when b squared minus 4ac is greater than or equal to 0. So when this number is positive. This number over here is also called the discriminant sometimes. I'll leave you with two questions that you can do if you aren't too tired from doing maths, or if you want some practice. Here, given that x plus 1 over x equals 13, find x squared plus 1 over x squared. I don't recommend you solve for x. Try and find another method of doing it. And here, prime factorize 3 to the power of 8 minus 2 to the power of 8. Don't calculate 3 to the power of 8 and minus 2 to the power of 8. Try and find a clever way of doing this, and that should be good practice. And with that, that's the end of intermediate algebra day 1.